Okay, today we derived the differential form of the momentum equation, and the starting point for this was to think about momentum equation applied to a small box in the interior of the fluid. So that's our control volume for the purposes of the momentum equation, and so our momentum equation in the x direction from a control volume perspective is just the sum of the forces in the x direction is equal to the time rate of change of mass times velocity for the control volume, that's v sub x, maybe I'll make that into a u, so m times u, plus the fluxes through the control surface of the x momentum. And so we have v dot dA representing the volume flux, and then rho times u being the momentum being carried by that. Now, when we take the differential form of this, we end up dividing by the mass and manipulating to great extent. The end result gets reversed in terms of its presentation to where we move the unsteadiness to the left-hand side, and we say du dt, plus then we have our convective acceleration terms, u du dx plus v du dy and w du dz. So this is the total acceleration. We have the local acceleration and we have the convective acceleration terms. The right-hand side are the forces. We have the normal force, minus 1 on rho, that's the density rho times dp dx, density, plus then a viscous term, which is nu times d squared u dx squared, plus d squared u dy squared, and the second derivative with respect to z. Finally, if there is gravity acting in the x direction, we have g sub x. Now, to map that to the terms in our control volume-based conservation of momentum equation, we have unsteadiness becomes unsteadiness, obviously. The flux terms are in differential form the convective accelerations. Then the right-hand side represent the forces, and so these forces all become the right-hand side. So what are these forces? We have the normal stresses, the normal forces. We have the shear forces due to viscosity. And we have the weight of the fluid. And together then in differential form they take on these units of acceleration throughout. Now this is just the x component. In the y and the z directions, what we would have to do is change a few elements here. And I'm going to circle in pink what needs to change when we switch components. And so these four u's on the left-hand side would become v or w for the other components. The d by dx and the g sub x become y or z, and then finally in the shear forces it's these velocities that would become v or w. And so with that we would have three equations for u, v, and w, and those three equations are known as the Navier-Stokes equations. Combined with mass conservation, which in differential form is the continuity equation, dv dy plus dw dz equals 0. These are four equations for the unknowns u, v, w, and the pressure P.